So we're going to go ahead and learn about entropy and the second law of thermodynamics. All right, a spontaneous process can be endothermic or exothermic, so there has to be another force that's there to help spontaneity, that determines spontaneity. And any ideas what it is? Entropy. Okay, entropy is a term coined by Rudolf Clausius in the 19th century. Good to know, just a fact. He was convinced that the significance of the ratio of heat was delivered and was ratio to the temperature it was delivered at. That's kind of bad wording. So it's related, it's the measure of the heat, Q, to the temperature, T. So we're going to write our equation, delta S equals Q over T. Heat over temperature. It's the ratio of the heat to the temperature at which it was delivered. Okay. But delta S, entropy, what we talk about is related to the modes of the motion in the molecules, and we call it randomness, right? Okay, so if I were to open this valve, what's going to happen? It's going to go to the A side. Why? It has more room, but it becomes more random. Okay, and if it becomes more random, the universe likes things to become more random. Okay? So entropy can be thought of as a measure of the randomness of a system. That's what I put on number 1. Also, you know, put a star by it, like this is important. The measure of randomness of a system. Like total energy and enthalpy, entropy is a state function. What does that mean? Do you remember? State functions, we only care about the beginning and the end. We don't care how we got there. If we take a straight line or if we take a curvy road, we don't care. We care about where we started and where we end up. Okay? So we're going to have this equation. Delta S, the change in entropy, is equal to S final minus S initial. So for a process occurring at a constant temperature, the change in entropy is equal to the heat that would be transferred if the process were reversible, divided by the temperature. We already wrote this down. You're going to have 3 equations of delta S equals that you have to use. Okay. Temperature has to be in what? Kelvin. So let's do an example. You could just put heat over temperature on your words. We already wrote it down once. You can write it down again. You ready? Delta S equals Q over T. So we're going to do this example. And it says, an element, mercury, is a silvery liquid at room temperature. The normal freezing point of mercury is negative 38.9 degrees Celsius. Its molar enthalpy of fusion is 2.311 kilojoules per mole. What is the entropy change of the system when 50 grams of mercury freezes at the normal freezing point? Okay. So first we have to find Q, right? Delta H of fusion is for what? Freezing and melting. Look at the units. 2.3 2.331 kilojoules per mole. So what do we have here? We're just kind of writing down 50 grams. Do these go together? This is how much, yeah, this is how much energy for 1 mole. We need to know what about 50 grams. So what do we have to do? Yes, so I'm going to erase so I have more room. So you're going to have to go 50 grams of mercury. And how many grams are in 1 mole of mercury? 200.6, yeah. 200.6. Now we're in moles. Okay, get an answer. What'd you get? 0.249. 0.249 moles. Now what? This is our delta H, which is kilojoules per mole, so we can multiply that, right? 2.331 kilojoules per mole. And we've canceled our moles, so we're in heat, right? Q and delta H are almost the same thing. So what do we get? Yeah. Oh, I got 0.571. 0.581. Okay, 0.581 kilojoules. Now we have to convert that to joules. That's pretty easy. How many?
Do we multiply 0.249 times 2.33?
Yeah. 581 joules. Okay, if we are a silvery liquid, we're a normal freezing point. We're freezing it. Negative or positive? Negative. Okay. Now, what do we divide that by? That's our Q. Divided by your temperature in Kelvin, which is what? Yeah, 234.3, right? And what do you get, Kelvin? Negative. 2.48 joules per Kelvin. That is our answer. I want you to write this. Delta S's units are joules per Kelvin. Just make a note of that somewhere. So that's pretty easy, right? So the only thing you didn't really know, and I kind of led you through, is that you have to get it to joules. Okay, so now you know delta S has to be in joules per Kelvin. Other than that, easy? All right. So now we're going to learn about the second law of thermodynamics. The second law of thermodynamics states that the entropy of the universe increases for spontaneous processes. And the entropy of the universe does not change for reversible processes. We're going to write this in other words and discuss it a little more. In other words, for a reversible process, delta S of the universe equals delta S of the system plus the delta S of the surroundings, and it's all equal to 0. Because for reversible processes, it is 0. It does not change. For irreversible processes, it is greater than 0. Irreversible processes are spontaneous. Or spontaneous. It's better if you say spontaneous. Things are irreversible. So let's do an example of each one. If it is a hot day outside, well, if it's just a normal day outside and we have water in a bowl, right? Spontaneously, what happens? Some of it's going to turn to a gas and some of it's going to turn back to a liquid. That's reversible, right?
Yes.
At the surface, some of it's going to be going to gas, some of it's going to be going to liquid. It does not change the randomness of the universe, because every time one of these goes to a gas, one of these comes back to a liquid. So nothing's changing, right? Reversible. Now, if we have an irreversible process like if it's hot outside, like really hot, and ice is melting, right, into water, it becomes more random. Think about it. Ice cube is structured, right? It's a cube. Or ice is structured, even if it's not a cube. Ice is structured. Water, not as structured. So that's increasing the randomness of the surroundings. And it's hot outside. Is it automatically going to go back this way? No. So we're releasing more entropy to the universe because it's becoming more random. Does that make sense? Some of you are nodding yes, some of you are just sitting there. All right. So this means that as a result of all the spontaneous processes, the entropy of the universe is always increasing. Okay, so for an isolated system, a reversible process, delta S equals 0. You better put isolated system. Isolated system. In an isolated system, for a reversible process, delta S equals 0. For an irreversible, delta S is greater than 0. Now this is the delta S of that system, not of the universe. We're talking about that system. So if I have an isolated system that's completely separated from everything else, like that closed container of gas, right? It's open right here. Hold on. Oops. Like we have that gas container, right? It's separated from everything else. If it's reversible and it's open and there's gas on both sides, if there's already gas on both sides, right? Does it change the entropy, the randomness? No. Every time a molecule goes from here to here, one's going from here to here, right? Nothing's changing. Now, if we have that same system, that isolated system, I know my artwork is amazing, and you have gas only on this side, it looks like kidneys. If you have gas only on this side and there's a valve, and then I open that valve and it's going to come over here, right? Is that reversible? No. We can't magically make all this go back. So what happens to the randomness? If I open that valve, it becomes more random, right? They're spread out. They're going crazy. So delta S is greater than 0. Good examples? So an increase in randomness is delta S is positive, and a decrease in randomness, delta S is negative. I think You want to know my silly way of remembering this? Delta S is like silliness, randomness. If it gets bigger, it's more random is more silly. That's just how I remember it. Positive. Okay? You know, I always have goofy ways of remembering things. Okay. We're nearly done. Here we go. Okay, so entropy and on the molecular scale. My ears are Ludwig Boltzmann described the concept of entropy on the molecular level. So he looked at specific molecules and how they moved and said, is this more random or less random? What's happening? Okay? He looks angry in that statue. I think he was not a happy man. All right. Temperature is a measure of the average kinetic energy of all the molecules, right? Keep that in mind as we go over these things. Kinetic energy is movement. So molecules exhibit several types of motion. The first one is translational movement, which is movement of the entire molecule from one place to another. So I'm going to draw a picture of a molecule. There's a molecule. It's a cute little flower looking one. And if it's translational movement, that means it's moving like this. The whole thing is moving somewhere else. Okay, it's a gas and it's bouncing off the walls. Okay? That's something you'll use in physics, translational motion. The next one is vibrational motion, which means it's the periodic motion of the atoms within the molecules. So here's a good picture of that. Normally it looks like this, and then it can bend, and then it expands, or the bonds might shift a little bit. See how these bonds are shifting a little bit? So molecules are moving. Even after we make a molecule out of atoms, they're still going to shift around a lot. That's vibrational motion. And then the last one is rotational motion, which means they spin around. Right? They rotate about an axis. Oh, really? Okay, so Boltzmann, looked at the motion of a sample of molecules at 1 second. So if you took a picture of the molecules, right? If you could use a camera and take a picture of the molecules, would they all be the same? No, because some of them have moved. Some of them are in different shapes. Some of them are rotated differently, so they're all moving around. But if you take a picture at 1 second, this is what you call a microstate of a thermodynamic system. So what most of it is doing. Okay, yes, there's going to be little differences, but overall we get the total energy from all those different changes. So how is entropy going to change for different molecules, and what does this have to do with entropy? The number of microstates and the entropy increases based on the following 3 factors. The first one is temperature. Why? Because if we increase the temperature, what happens? It moves faster. It's going to translational motion, right? It's going to move around. It's also going to move the particle or the atoms within the molecule more because they have more kinetic energy. What about volume? Why would entropy increase when we increase volume? There's more room. Very good. There's more room to move around. That's like you. If you're crowded in the car with your siblings and you're on vacation and you're driving somewhere and you're like, oh, and then when you get out, you just kind of go crazy, right? You're like, I have to move. Been crowded. Okay, and then the next thing is the number of independently moving molecules. So if we have more molecules, we're going to have more entropy. Because they're going to bump into each other, right? Other things that affect entropy. Entropy increases with the freedom of motion of molecules. This is water in what state? Solid, that's right. It's in the solid state. It's very structured. Do you see that? It's very structured. What happens if we melt it to a liquid? It's going to have more, it's going to have more freedom, right? It's going to be able to move around more. It's going to increase in randomness. What if it's a gas? Yeah, it does whatever. It moves wherever it wants. It goes crazy. So this is our rule. Gases have more entropy than liquids, and liquids have more entropy than solids. The next thing is solutions. In general, if we dissolve a solute in a solvent, entropy increases. Look at how structured this solid is down here. Very structured, right? As it dissolves in water, what happens? Spread apart, they can move more, they have more freedom, more randomness. Bigger, an increase in delta S with dissolving. Okay. If we have a reaction and we increase gas moles, so that's what we're going to look at next. So we have a reaction. Entropy increases when gases are formed from solids and liquids. So if we had a reaction with a solid on this side and a liquid, and we made a gas like magnesium and hydrochloric acid, right? And we make a gas, which would be hydrogen gas. We just increase the entropy because it became more free to move around. Okay. Liquids or solutions that are formed from solids increases the entropy. The number of gas molecules. So I'm going to give you an example of that one. If we had, right here, this example right here. If we're going this way, are we making more or less gas molecules? Over here we have 3, over here we have 2, so our delta S went down, or it's negative. Okay, that's kind of the same as this, the number of moles. All right, all we have left is 2 examples, and then you can do whatever you want. So, do y'all need to take a break? Keep going. All right. Oh, write this down. The entropy of a pure crystalline substance at absolute 0, you have to write this to the side, is 0. If we're at absolute 0, which is 0 Kelvin, what happens? No, all particles stop moving. If all particles stop moving, can there be any entropy? No. So it's 0. That's how I'm writing it. That's a J. 0 Kelvin is 0 joules per Kelvin. There's no motion. All right, let's do these easy peasy examples, and then you do not have homework today because these are easy, so we'll put them on tomorrow's homework, okay?
What are we doing Friday, Miss?
We'll probably take a quiz. We'll be doing lessons. Maybe, I don't know. Okay, so predict whether delta S is positive or negative for the following. So let's look at number 1. It goes from a what to a what? Liquid to a gas, so that increases silliness, right? Increases entropy.
Is that an S?
Yeah, sorry. Positive delta S. Or you can stay as long as you're quiet. We have a few more slides to record. Okay, what about this one?
Liquid to a solid.
It's going aqueous to a solid, and also it's going from ions to a compound. So what do you think? Decreases, negative delta S. It becomes less silly. Right, less random.
Love you, Miss Parker.
Love you too. Bye. Okay, what about this one? Over here we have a solid and a gas, but it makes only a solid. So we're losing what? We're losing gas. So what do you think? Decreases, negative delta S. Okay, what about this one? Gas, gas. 1 mole, 2 moles. But this are 2 separate moles, right? These are 2 moles together. It's going to stay very close to the same. It will slightly decrease. It's very close to the same. We're going to put, in fact, you know what? We're going to put close to the same. It's hard to predict. I don't even know if I'd predict it at all. You have to be quiet.
You're recording?
Yeah.
Oh,
Okay. All right, let's look at the next one. Y'all are good at these. Here we go. Which one has greater entropy? So we're going to circle them. Which one would have greater entropy? 1 mole of sodium chloride solid or 1 mole of hydrochloric acid gas? Gas. Okay. 2 moles of hydrochloric gas or 1 mole of hydrochloric gas? 2 moles. More moles. 1 more mole of hydrochloric gas or 1 mole of argon gas? Ooh, this one's harder. What do you think? Now we have to look, okay, there's 1 mole, there's 1 mole. They're both gases, right? But what does HCl have that argon doesn't? 2 atoms, and what can those atoms do? Move. So which one?
If you would
HCl.
please stand and join me for the